Swayam Prabha. Digital India. Educated India.
Hello. In today's lecture series, rather starting from today's lecture series, what we are going to study about is a very fundamental, very important aspect of engineering analysis. Over the next several lectures, what we are going to understand about is about thermodynamics. Thermodynamics is a very fundamental subject which plays a very significant role in understanding of engineering systems. And in this course that we are currently studying about, that's on Introduction to Aerospace Propulsion, thermodynamics is a very fundamental science that needs to be understood very carefully. It's very important that we understand some of the very fundamental aspects of thermodynamics, basically because thermodynamics forms the basis for understanding and also design and development of engineering systems. And in the kind of systems that we are going to study in this course, that is related to aerospace propulsion, thermodynamics is the basic subject that needs to be understood thoroughly. So, let us take a look at what we are going to study or understand in this particular lecture. Now, this lecture is on very fundamental aspects of thermodynamics. We shall get introduced to basic aspects of thermodynamics. So, introduction to thermodynamics, its significance, and some of the basic terminology that we are going to use in thermodynamics is what we shall cover in this course. So, if you take a look at what are the contents of this particular lecture, we shall first get introduced to basic thermodynamics. We shall understand the scope and method of thermodynamics. We shall define basic terms and concepts. Some of the basic concepts that we shall be understanding and studying in this course will include system, surroundings, boundary, and the universe. We shall then analyze the different types of systems that are in existence or that you can define for a particular system under investigation. We shall understand property of a system, what we mean by property of a particular system. We shall also understand the state of a system and about equilibrium of a system and its state. We shall also understand a very basic concept known as the state postulate, which helps us in defining the property of a system. We shall, towards the end of the lecture, we shall understand and explore a few basic terms like process, path, and cycle for any particular system. Now, thermodynamics is a very old subject, probably as old as existence of mankind itself. The basic reason is that man has always wanted to convert available heat into power, and this has been an endeavor of mankind since time immemorial. So, thermodynamics as of today is defined as the science of energy, and the basic reason for this is that thermodynamics as a word originates from two Greek words known as thermi and dynamis. Thermi, which means heat in English, and dynamis means power. So, basically this means that thermodynamics implies conversion of heat into power. So, this is a very basic requirement that man has always been endeavoring towards, to convert heat into power and in a very efficient way. So, thermodynamics is a science which deals with this conversion of heat into power, and that is why it is a very basic science in itself. For example, the particular course that we are currently undergoing deals with introduction to aerospace propulsion. So, propulsion basically means providing power to a particular vehicle. So, this power would involve conversion of one form of energy into another, and that is what basically thermodynamics deals with. So, thermodynamics is basically a tool or a mechanism by which you can understand a system which is converting heat energy into power. And therefore, thermodynamics in one sense encompasses all forms of heat conversion into power. And what we shall try to understand over the next several lectures is that what are the different ways by which you can understand a particular system which is basically trying to convert one form of energy into another. So, thermodynamics basically helps us in providing an understanding of the nature and the degree of energy transformations. So, we would be able to towards the end of this lecture series on thermodynamics, we shall be able to analyze a particular system which is basically trying to convert heat into power output. And another very important aspect of thermodynamics is that thermodynamic laws, as we shall see little later, are fundamental laws of nature. These are like the laws of Newton, which are also considered to be fundamental laws of nature. And therefore, it is very important that we understand the meaning and the implications of the different laws of thermodynamics. So, as we shall see later on, there are 4 laws of thermodynamics that we shall study, named 0th law, the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. So, these 4 laws of thermodynamics are very fundamental in nature, and therefore, they are also considered to be fundamental laws of nature, which has to be followed and cannot be violated. So, these thermodynamic laws cannot be violated, and this is the basic reason why it is important that we understand the implications of thermodynamic laws, because very often one comes across different systems which are being proposed by different people, which can convert heat into power, but in some sense or the other they violate one of these thermodynamic laws, and therefore, these systems are by themselves, by their very design, not feasible. And so, a thorough understanding of thermodynamic principles and its laws are important in our understanding of engineering systems, and also to evaluate the feasibility of new concepts and designs. So, let us take a few examples of thermodynamic systems. For example, if we would like to heat water in a kettle, or we would like to burn some fuel in a combustion chamber of an aero engine to propel an aircraft, or you would like to cool a room on a hot humid day, or perhaps you would like to heat up your room on a cold winter night. So, these are examples of common occurrences in daily life. So, in all of them, you would be interested in knowing what is the smallest amount of electricity or fuel that will be needed to carry out the above. Now, these are very simple examples. There could be numerous other examples, like for example, you are driving a car, you are basically converting fuel, which it could be petrol or diesel, into power output for driving the car forward, or you could be, for example, preparing a particular dish in a pressure cooker. So, you are converting energy into a different form. So, you are basically dealing with conversions of energy day in and day out. Another very important example of a thermodynamic system is a human body. Now, all human bodies convert energy in some form into another form. So, the energy that we take in is the food that we take, and this food is converted to energy in some other form, which enables us to walk or run and do daily activities in a normal way. So, that the human body itself is a very complex thermodynamic system, and we shall understand some of these aspects as we progress along these lecture series. Let us take a look at some more examples of thermodynamic systems. Now, when we burn some fuel, as I was mentioning a little while ago, we are burning some power, that is coal or gas, in a power plant to generate electricity. or you burn petrol or diesel in a car engine, what is the largest amount of energy that we can get out of these efforts? You would be very much interested in efficient conversion of fuel into power output. That is one of the major goals of an engineer in a modern day, because he would like to have his system as efficient as possible, that converts the amount of available energy into work output in the most efficient way. So, thermodynamics is a science which allows us in answering many of these questions, and in the current day scenario, it is very important that we are able to design systems which are as efficient as possible. Thermodynamics is a basic science which helps us in converting fuel into power output, and for that matter involving any other energy conversion, it is important to understand the basic thermodynamic principles. So, let us move on further and understand some of the basic terminologies that we shall use throughout this course. Now, there are two different ways in which you can analyze a thermodynamic system. One of them is known as the macroscopic approach, which is also referred to as the classical thermodynamics. So, the thermodynamic science or the approach which deals with a macroscopic sense of systems is referred to as the classical thermodynamics. So, the advantage of a macroscopic approach is that it does not require the knowledge of the molecular level of the system. You can analyze a system as a whole, and you do not need to know the behavior of individual molecules in a system, which can be quite complicated. And so, macroscopic approach does not require knowledge of the molecular level. So, macroscopic approach is an easier approach, it is a more direct approach, especially in the case of engineering systems, where you would not really want to bother about the molecular level dynamics, and you would like to analyze a system as a whole, as a group of molecules rather than at their individual level. And it is because of this reason that we are going to follow the classical approach that, or the macroscopic approach, or classical thermodynamics in this course. The other approach, on the other hand, is the microscopic approach. So, microscopic approach involves deeper understanding of the molecular level of a system and taking a look at the individual behavior of molecules. And therefore, as we are understanding the molecular level dynamics, it is far more complicated, and it extensively uses the kinetic theory of gases. So, this particular approach is also known as the statistical thermodynamics. So, as the name itself refers to, statistical thermodynamics obviously will involve exhaustive use of statistical principles, because you are understanding or trying to understand the system on a molecular level. So, we are not going to approach thermodynamics in a statistical sense, we are going to take the macroscopic approach or the classical thermodynamics approach in this course. So, the other principle or the assumption that we are going to make is known as continuum. Continuum refers to the continuity within a system. I will explain that shortly. Now, as we are all aware, matter is made up of atoms which are widely spaced, especially when it comes to the gaseous phase. Now, in classical thermodynamics, we would want to disregard the atomic nature of a substance and view it as a continuous homogeneous matter with no holes or void, that is, it is a continuum. So, this is what I was mentioning a little while earlier, that in classical approach you do not want to look at the molecular level of a system, but you would like to look at the system as a whole. So, the continuum approach is what we shall be following. So, continuum idealization allows us to treat properties as point functions and to assume that the properties will vary continuously in space with no jump or discontinuities. So, what is a point function and its implications we shall understand a little later when we look at properties and systems. So, continuum approach is the approach that we are going to follow in this particular course, because we are looking at the classical thermodynamics approach and not the statistical thermodynamics approach. Just let me explain what we mean by the continuum approach and with a small example. Now, for example, if you look at oxygen as a particular gas that we are interested in, as you see here in this bounding box, we have oxygen as the medium present there. And as we know that in the gaseous phase, there is a lot of random motion or Brownian motion of the molecules. And for oxygen, which is at pressure of 1 atmospheres and 20 degrees Celsius, there are estimated to be 3 into 10 raised to 16 molecules per millimeter cube of volume. So, you can see that there are so many number of molecules in a very small volume of oxygen. But in spite of that, as this illustration shows, which is obviously highly exaggerated, between the molecules of oxygen you can still see a lot of void or free space. But the good thing here is that in spite of the presence of these large gap between the molecules, there are enough number of molecules within a very small volume to enable us to consider this as a continuum. And therefore, in classical thermodynamics, we shall be dealing with systems which are in continuum. We shall not look at the rarefied aspects of a system, which is a different study on its own, which is usually covered using statistical thermodynamics. So, a continuum approach is yet another assumption that we are going to take in thermodynamics. Now, what we are going to do over the next several slides, which we shall explore today, is to understand some basic terms which we shall be using very continuously quite often in this course and in subsequent courses. So, it is very important for us to understand the basic meaning of these terms. Now, one such term that we shall use very frequently is a system. So, what do we mean by a system? So, system by definition is a quantity of matter which we have chosen for study. Now, since we are dealing with macroscopic approach, it is a macroscopically identifiable collection of matter on which we focus our attention. So, system is a quantity of matter in space which we have chosen for our study. For example, if we are trying to analyze an engine, aircraft engine, and to see the thermodynamics of an aircraft engine, so we would like to choose the engine as the thermodynamic system, because that is the quantity of matter in the space which we are interested in at a moment. So, we would like to choose that particular system which is the aircraft engine in this example as the system which is under consideration. Now, what is around the system is referred to as the surroundings, and so surroundings is the matter which are in the immediate vicinity of the system and which have some amount of effect, perceptible effect on the system. That is, if the system we are considering, let us say the aircraft engine for example, the air which is just in the vicinity of the aircraft engine is referred to as the surroundings, and what separates the system from the surroundings is referred to as the boundary of the system. So, a boundary of a system demarcates or separates the system from its surroundings, and there could be boundaries which are of different types, as we shall see some examples little later, that a boundary could be either fixed or it could be movable. You could also have boundaries which are real, that is physical boundaries, or you could also have an imaginary boundary depending upon the convenience of analysis. And the system, the surroundings and the boundary put together constitute what is known as the universe. So, system refers to this matter in space which is of interest to us and which we are considering for our analysis. Surroundings is the environment or mass or region which surrounds a system, which is in the immediate vicinity of the system and which has some perceptible effect on the system. Boundary is one which separates the system from its surroundings, and universe is the system and its surroundings including the boundary put together is referred to as the universe. Now, let us look at an example here. What is shown here is a system which is demarcated by its boundary. So, what you see here indicated is the boundary of the system. So, this boundary separates the system from the surroundings. So, surroundings refer to that matter of space which is in the vicinity of the system and which has some perceptible effect on the system, and boundary is the one which separates the system from its surroundings. Now, a system could be of different types depending upon the nature of the system itself. Now, depending upon what type of system it is, it could be classified as a closed system. A closed system is one where there is no mass transfer, but there is an energy transfer that is possible. So, closed system is what is shown here in the example. What you see here is what we shall see this example very often in thermodynamics. This is referred to as a piston and cylinder assembly. So, what is seen here bounded by these lines are is the cylinder, and what is seen here is the piston. So, a piston and cylinder assembly, it's a system which we shall refer to very often in this course, and as we shall see little later after several lectures, is that this is very similar to what you see in automobile engines. All automobile engines operating on either spark ignition system or compression ignition systems would have a piston and cylinder assembly. So, that is an example which we shall refer to very often, because that is one of the common types of systems that we are familiar with, which generate a power output. So, as a closed system is one across the system boundaries of which there can be only energy transfer, but there cannot be any mass transfer across the system boundaries. An open system, on the other hand, is one across which there could be both mass transfer as well as energy transfer. So, open system involves the interaction of the system with its surroundings through mass as well as energy, and an isolated system is one across the system boundaries of which there could be either no mass transfer as well as no energy transfer. So, an isolated system does not interact with its surroundings through mass or energy interactions. So, these are the different types of system that are possible. Closed system, only mass transfer not allowed, energy transfer is allowed in a closed system. Open system, both mass as well as energy transfer is permissible, and if a system has no mass or energy transfer, such a system is known as an isolated system. Now, we shall look at some examples of systems which fall in either of these categories. Now, we shall take a look at those examples after we understand how do we choose a particular system. Now, we must choose a system for each and every problem that we are interested in. This is important because if you choose a system very carefully, it will help us in obtaining as much information about the system as possible. So, it is very important that we choose a system which is appropriate for the particular problem that we are interested in. So, this means that choice of a system would be quite obvious in some cases, but in some cases obviously it will not be that clear in the beginning. So, a system must be chosen in case the system choice is not very obvious. It must be chosen carefully depending upon what is the purpose of this particular thermodynamic analysis. And when we choose a system, the boundaries of the system could be either real boundaries or physical boundaries, or it could be imaginary boundaries. So, that again depends upon what is it that we are trying to analyze from a particular system. And the other aspect of boundaries is that you could have boundaries which are either stationary or fixed, or you could have boundaries which are movable or which are in motion. So, you could have a system which could have a combination of these different properties, that it could have a boundary which is fixed, or it could have a boundary which is movable, it could have a real boundary or a physical boundary, or it could have a boundary which is imaginary in nature. So, we shall get more information on these aspects of a system as we take a look at some examples which will help us in explaining what these actually mean. Now, let us look at one example of a closed system which has a movable boundary. Now, what you see here is a closed system, and it is a closed system because there can be only energy transfer across the system boundaries. There is no mass transfer across the system boundaries, and therefore, it is a closed system. And what you see here are fixed boundaries of the piston cylinder arrangement. Remember, I had mentioned about the piston cylinder example, which we shall see very often. So, this is the same piston cylinder example we are coming across. So, this cylinder consists of a particular gas which has a particular mass of 2 kgs and let us say a volume of 1 meter cube. Now, the cylinder boundaries are fixed because they do not move. Now, if you were to add energy across the system boundaries, remember a closed system, it is possible to have energy interaction across the system boundaries. So, there is energy transfer because you are heating up the cylinder. So, there is an energy interaction across the system boundaries. Now, the piston on the other hand forms the movable boundary. So, as you add heat to the system, it causes the gas to expand. So, as you can see here, the mass of the gas still remains 2 kgs because there is no mass transfer across the system boundaries, but yes, the volume of the gas increases because you are adding energy. So, as the volume of the gas increases, the piston has moved to a new location, and therefore, this constitutes a moving boundary of the system, and the cylinder walls form the fixed boundary of a system. Now, yet another example here. Here we have an example of a control volume, which is basically an open system, which has both real as well as imaginary boundaries. So, the example that is shown here is that of a nozzle. A nozzle is a section which is again very often used in engineering systems, and is a system which is used for accelerating a flow in a subsonic Mach number flow. What is subsonic will become clear little later. So, in subsonic flows, a nozzle which of the geometry which is shown here can lead to acceleration of the flow. So, in this nozzle, the walls of the nozzle form the real boundaries indicated by these dark black lines form the real boundaries. And what about the inlet and exit of the nozzle? At the inlet and exit of the nozzle, we can define imaginary boundaries. So, what you see here are the imaginary boundaries of the nozzle. So, these form the imaginary boundaries of the nozzle which bound the control volume, and the real boundaries are shown by these dark lines which are on the periphery of the nozzle. So, this is an example of an open system. An open system is also very usually referred to as control volume, a control volume which has both real as well as imaginary boundaries. Now, let us look at an example which combines the previous example as well as this example in some sense, because you have an open system here with a moving boundary. So, we had already seen an example of an open system which has real and imaginary boundaries, and here we have an example which has of an open system, that is a control volume which has both fixed boundaries as well as a moving boundary. So, the cylinder volumes, as I had mentioned earlier, walls of the cylinder constitute the fixed boundary of the system, and the piston on this side constitutes the moving boundary. And this is a control volume, that is an open system, because there is mass transfer across the system boundaries in addition to energy transfer. So, this is an example of an open system which has a fixed boundary as well as a moving boundary. Yet another open system here. This is an example of let us say a storage water heater which is used for heating water, and in this case we have water coming in, which is cold water coming in from one side of the control volume, and hot water which gets heated up inside the water heater comes out through another outlet. And now you can see that there is mass transfer across the system boundaries, there is also heat addition inside the system, and that therefore, it qualifies to be called an open system or a control volume. And what bounds the control volume is referred to as the control surface. So, control surface acts as the boundary of a control volume. And so, this is an example of a control volume, an open system which has one inlet and one exit. So, it is obviously possible that there are control volumes or control systems which have multiple inlet and multiple outlets. And so, many of these examples we shall see as we analyze different engineering systems, especially an aircraft engine, that is an engineering system which is of interest to us in this course. We shall understand the working of such engineering systems through thermodynamic analysis, which will require us to use many of these concepts of defining the system, its boundaries and its surroundings. Now, moving on, we shall now understand what is meant by a property of a system. Now, if we were to define a particular system, we have now understood how we can define a particular system. Each engineering system requires to be defined in terms of its boundaries and its surroundings. And now, how do you characterize this particular system? So, a property refers to any particular characteristic of a system. Now, there are different ways in which you can define a property. So, a property is any characteristic that defines a particular system. The property could be temperature of the system, it could be pressure, it could be density or mass and so on. And therefore, these are properties which characterize a particular system. Now, the defined properties could either be intensive property or it could be an extensive property. Now, the property could be intensive if the particular property is independent of mass. For example, temperature or pressure, these are properties which do not depend upon the mass or size of the system, and therefore, they are referred to as intensive properties. Now, extensive properties on the other hand are those properties which depend upon the mass or size of the system. Some examples of extensive properties are mass itself, obviously it depends upon the size of the system. Volume of a system is again an extensive property, because it depends upon the mass or size of the system. Momentum associated with a particular system again depends upon the mass, and therefore, that is also classified as an extensive property. Now, there are properties which extensive properties taken per unit mass are also referred to as specific properties. For example, volume, which is an extensive property taken per unit mass, is referred to as specific volume, and energy, for example, is again an extensive property. Energy per unit mass is referred to as specific energy, that is again a specific property. So, these are extensive properties per unit mass referred to as specific quantities or specific parameters. Now, let us take a look at an example which will help us in explaining what are intensive and extensive properties. So, what is shown here in this example is a system which has different properties which have been defined here in terms of its mass, volume, temperature, pressure, density, etc. Now, if we were to split the system exactly into half, like what is shown here on the right hand side. So, we have a splitter which splits the system exactly into half. Now, let us look at what happens to the different properties of the system. Now, there are certain properties of this system which would now change, and there are certain properties which will remain the same. Now, those properties which change are the mass and volume. So, as you split the system into half, the mass of the systems become half and volume also becomes half. But if you look at temperature, pressure or density, these do not change even if you have split the system into half. So, these are referred to as intensive properties, because they are independent of the size or mass of the system, whereas mass or volume are extensive properties, because as you split the system into different portions, the mass or volume of the system also changes. So, this is an example of a system which has been defined in terms of both intensive as well as extensive properties. Now, very often you would have to define a system by using some of these properties. In fact, you will need a certain set of properties, as we shall see a little later, that are required to completely define the condition of the system. Now, a set of properties which define the condition of a particular system at a particular instant of time is referred to as state of a system. Now, a state of a system gives complete description about what is the condition of that particular system at an instant of time. Now, and at a given state, all the properties of the system would have fixed states or fixed values. That is, if you have defined a state of a system with a certain properties, these properties will remain fixed for that particular state. Now, if one or more of these properties change, then this operation is known as change of state. So, any operation which involves change of one or more properties of a system is referred to as change of state of the system. And let us look at an example which will help us in understanding this. Now, here we have the piston cylinder example again. On the left hand side, we have the system which has a mass of about 3 kgs, let us say, temperature of 25 degrees Celsius, a volume of 2 meter cube. Now, this defines the state of this particular system at particular instant of time. Now, if one or more of these properties were to be changed, then that defines yet another state of the system. So, on the right hand side, what we can see is that the mass of the system is fixed, because it is a closed system. So, mass does not change, and in this example, let us say the temperature is also fixed, but because the piston has moved away from its initial state, the volume has changed. Now, because the volume has changed, the system has now moved on to a new state. So, this right hand side shows the system at a different state than what it was previously. So, this is an example of a system, the same system, which is existing in two different states by virtue of change of one of its properties, that was the volume in this particular example. Now, in thermodynamics, when we analyze different systems and what the state of the system is, etc., we would be dealing with equilibrium states, and equilibrium is implying that the state of the system is in a particular balance. So, basically the word equilibrium implies a state of balance, and for a system to be in a state of balance, it is essential that there are no unbalanced potentials or driving forces within the system. So, for an equilibrium state, the system does not experience any change when it is isolated from its surroundings. So, a system that is in complete equilibrium will not undergo any change when it is isolated from the surroundings. Now, in thermodynamics, we shall be dealing with different types of equilibrium. A system could be in mechanical equilibrium, it could be in thermal equilibrium, chemical equilibrium, or phase equilibrium. So, in thermodynamics, we could be dealing with different forms of equilibrium. A system could be in thermal equilibrium, a system could be in mechanical equilibrium, it could be in phase equilibrium or chemical equilibrium. Now, a system is referred to be in thermodynamic equilibrium if all these conditions are satisfied, and unless all the conditions of equilibrium in terms of mechanical, thermal, chemical or phase are not satisfied, a system is not said to be in thermodynamic equilibrium. Now, a system which is in thermodynamic equilibrium does not deliver any useful work. Now, this may come as a surprise, basically because you would expect that if a system is in thermodynamic equilibrium, well, it should perform very efficiently. Well, that necessarily does not happen, because when a system is in thermodynamic equilibrium, as we have seen earlier, that there are no more driving forces or driving potentials. So, in the absence of any driving potentials or driving forces, there is no possibility of generation of work output. So, this will become, the statement will be more clear as we understand more concepts like work and heat transfer of a system. We shall be able to appreciate this point better as we understand work and heat transfer little later in further lectures. Now, let us look at what are the types of equilibrium. I mentioned that there are 4 different types of equilibrium that are possible. Thermal equilibrium, a system is said to be in thermal equilibrium if the temperature of the system is the same throughout the system. And on the other hand, a system is said to be in mechanical equilibrium if the pressure is the same throughout the system. That is, if the pressure within the system is the same everywhere, it is said to be in mechanical equilibrium. And if the chemical composition does not change with time, that is, there are no chemical reactions taking place, then it is referred to be in chemical equilibrium. And if the system consists of different phases, let us say a solid phase and a gaseous phase, when the mass of each of these phases reaches an equilibrium level, then it is referred to be in phase equilibrium. That is, for multi-phase systems, wherein you have different phases of the same system, either liquid gas or solid gas or all the 3 phases together, if the mass of each of these phase remains constant or it reaches an equilibrium level, it is said to have been in phase equilibrium. So, a system which has all these different types of equilibrium conditions satisfied is said to be in thermodynamic equilibrium. Now, let us look at one example of a system which is in initially not in equilibrium and then it has become come to an equilibrium state. So, the example shown here is that of a system which was initially having different temperatures in different parts of the system. You can see that the system has different temperatures ranging from 20 degree Celsius to 40 degree Celsius, and that keeps changing across the system. Now, for the system to be in thermal equilibrium, the temperature has to be the same throughout the system. So, after the system reaches thermal equilibrium, the temperatures are, as you can see here, are the same. It is 30 degrees Celsius everywhere. Now, in this example which is shown, it is just shown that the system is in thermal equilibrium. So, this does not mean that the system is in thermodynamic equilibrium. For this system to be in thermodynamic equilibrium, in addition to the temperature being same everywhere, it also has to satisfy the conditions for mechanical equilibrium, which means the same pressure throughout the system, or chemical equilibrium, which means no chemical reactions occurring, as well as phase equilibrium, that is, if the system constitutes different phases, all the phases should be in equilibrium. So, this particular example which is shown is that of a system which is in thermal equilibrium. So, in thermodynamics we shall be always dealing with equilibrium states of a system, and which means that it need not be essentially in thermodynamic equilibrium, but it could be in one of the different forms of equilibrium. It could be either in thermal equilibrium or in mechanical equilibrium and so on. And if you recall, I had mentioned little earlier that we need a certain number of properties to define the state of a particular system. So, how do we know what number of properties are needed to define a particular state? Now, it is not required that we define all the properties of a particular system. If you define certain properties of a system, certain number of properties, that itself will define the state of a system in totality. So, it is necessary for us to know what is the minimum number of properties that you would need to define a particular state of a system. Now, this is explained by what is known as the state postulate. Now, state postulate states that you can completely define the state of a simple compressible system by specifying 2 independent and intensive properties. Now, we have a new term here, simple compressible system. Basically, a simple compressible system refers to a system wherein there are no effects of gravity, electrical, magnetic fields or surface tension effects. That is, a system wherein there are no effects of electrical forces or magnetic forces, gravity effects or surface tension effects is referred to as a simple compressible system. So, according to the state postulate, For such a system, which is basically a simple compressible system, it is possible to completely define such a system by specifying just two properties which are independent and which are intensive. So, we have already seen what are intensive properties. Intensive properties are those properties which do not depend upon the mass or size of a system, and independent properties are those in which you can change one of those properties without affecting the other. That means that each of these properties are independent or mutually exclusive. So, according to state postulate, you can define the state of a system completely by just defining two properties which are independent and which are intensive. Now, let us explain this point further by an example. Now, the example that is shown in the slide is that of nitrogen, which is again housed within a piston cylinder assembly, and we can see that the state of nitrogen, for example, can be fixed by two independent intensive properties as per the state postulate. Now, here we have defined the state of nitrogen by defining it by its temperature and specific volume. So, both of these are independent properties and these are also intensive properties, which means that it is sufficient for us to define the state of nitrogen by these two properties. But on the other hand, instead of specific volume, you had decided to define it by temperature and pressure, then it is not basically defining the state of nitrogen, because temperature and pressure are not independent. That is, you cannot vary the temperature by keeping the pressure constant and so on. So, temperature and pressure depend on each other, and it is therefore not possible to completely define the state of a system by just defining temperature and pressure. So, you need two properties which are independent as well as those properties which are intensive to be able to completely define the state of a system. So, state postulate helps us in identifying number of properties which will be required to completely define or specify the state of a system. Now, let us now proceed further and define or understand a few more terms which we shall be very often referring to. One such term is known as process. Now, we have seen that a system which is in a particular state can move to another state if one or more of its properties change. So, a process is referring to any change or that a system undergoes. Process basically refers to any change that a system undergoes from one equilibrium state to another. And so, the series of states through which the system would pass during such a process is referred to as path of this particular process. And if the system returns to its initial state at the end of the process, then that is referred to as a cycle. A cycle is referring to a process wherein the initial and the final states are identical. So, process refers to change of a system from one equilibrium state to another, and as the system progresses from one equilibrium state to another, it could be through a series of different states. And so, these series of states through which the process has taken place is referred to as the path of the process. And if the initial state and the final state happens to be identical, it is referred to as a cycle. And let us take some examples which will help us in understanding what a process is and a path and a cycle. Now, we shall take a look at the classical example of the piston cylinder assembly, which we have seen throughout this lecture and in future lectures as well. Now, what is shown here is an example of a property change from state 1 to state 2. Now, what is shown here is that a system which has been plotted from change of state from state 1 to state 2. So, this change of state has taken place through this green line which is shown here, and which you can see that there are so many intermediate states or steps in between state 1 to state 2. So, this is referred to as the process path. Now, to explain this further, let us look at this piston cylinder assembly example. Now, the piston was initially at state 1, which is shown by this dotted line here. So, the initial state has a certain specific volume and a certain pressure P 1. As the piston is moving into the cylinder or as the system is compressed, the pressure rises because it is a compression process. The pressure will increase from state 1 to state 2, and in the process the specific volume reduces or changes. So, the new state, which is referred to here as the final state, is marked by 2, has a new specific volume V 2 and new pressure P 2. So, this is an example of change of state from state 1 to state 2 through a process which has been indicated by a process path. Now, if the same example we had the process which is coming back to its initial state, then this is referred to as a cycle. For example, if the piston cylinder assembly was initially at station 1, after the whole process it has come back, that is after an expansion, that is reduction in volume, increase in volume and reduction in pressure, and then further it is compressed back to its initial state. This is referred to as a cycle. That is, the initial state and the final state are identical. So, depending upon the type of process, we can usually classify the processes as different types, and usually, as we shall see little later, during a process we allow one of these properties to remain constant, and a process in which the temperature is constant or is held constant is referred to as an isothermal process. A process in which the pressure is constant is known as an isobaric process. A process during which the volume is constant is called an isochoric process. Process during which a property known as entropy is constant is called an isentropic process, and a process during which yet another property enthalpy which is constant is called an isenthalpic process. So, I have indicated question marks here against entropy and enthalpy, because at this moment you would probably be wondering what entropy and enthalpy are. We shall understand about these terms in very much detail during later lectures. So, a process during which a particular property is held constant is classified as a different process on its own. So, that brings us to the end of this lecture. So, let us quickly recap what we had gone through during this lecture. We had understood several basic thermodynamic concepts like the system, surroundings, boundary and the universe. We had also understood what are different types of system that are possible, like an open system or a closed system. We had understood what is meant by property of a system, that is, how do you characterize a particular system. And then we had also looked at what is meant by state of a system and what are equilibrium states of a particular system. Then we also understood what are the minimum number of properties that are needed to define the state of a system, that is known as a state postulate. Towards the end of the lecture, we also looked at what is meant by process, path and cycle. In the next lecture, what we shall look at, we shall understand what are meant by quasi-static processes. We shall understand the concept of energy and its different forms. We shall understand what is meant by internal energy and different types of internal energies. Then we shall also look at a combination property known as enthalpy, and towards the end of the next lecture we shall also undergo introduction to the zeroth law of thermodynamics and temperature as an outcome of the zeroth law of thermodynamics. So, these are aspects which we shall be covering in the next lecture.